Ladies and gentlemen, we have a request from an exam to do a problem that we might be seeing next week on our first test. This type of problem will be on your first test because this I got from fall 22. You will have a version of this question on your short answer. I will change the 8 molecules to new molecules, and that's the only change, which changes everything, you know, but doesn't change the fact you have to understand intermolecular forces to understand physical properties. We take intermolecular forces for granted in life. We shouldn't. They're very important. We'll do it from the small scale to the big scale. You take a shower in the morning. You get out of the tub. You don't put your shirt on right away, do you? Gosh, I hope not. You've tried it though. At least once in your life you tried. Putting on the shirt before you dry it off properly, it's not a good exercise. You can hurt your muscles. Why? That's only a thin layer of water on your body. What's going on that makes it so sticky to your body? It's like you try to pull the shirt off and it won't move. Adhesion. What, in particular, what kind of adhesion? Remember, water. And most shirts are things like polyesters or a cotton or a nylon or a dacron. And I want to tell you, every one of those, well, almost every one, has an oxygen that has a nice intermolecular force because it's a polar oxygen, like a carbonyl. What's the electronegativity of carbon again? 2.5, and the oxygen that's in a carbonyl, what's it? Electronegativity? 3.5. When you have a difference of 1.0, what is the type of bond we're talking about? The covalent bond. What's it called? Sorry, say again. Polar, and it's shared, so polar covalent. Okay. Now that in itself has a pretty good intermolecular force, right? It's called dipole. But the fact is, water has an extreme dipole because H is bonded to O in water, right? And what kind of intermolecular force can you have with that H and another molecule's oxygen? Hydrogen bonding. The lone pair on the oxygen gets in close to the hydrogen because the hydrogen's feeling a little positive, and there's an attraction to the oxygen because it's an electronegative atom. It's a negative thing. Okay? And even though those are small individual intermolecular forces, right? There's trillions of them on your back with that thin layer of water, which was almost no water at all. You thought you were dry. That's why you were putting your shirt on. You weren't quite, right? And it's just that accumulation of the little itty bitty forces is huge. Do you want a more profound example? Here's a more profound example. You go to the redwood forest in California. It's magnificent. You look up, you're at there's this tree in front of you that's 300 years old, and it's more than 100 feet in the air. And what's the only thing holding that tree up? What are the molecules that give a tree strength, period? Like, they're strong molecules by themselves, but they're not what make a tree stand up straight in the air. No, there's no nitrogen in the strength part of the tree. It's all cellulose. You know, wooden bat, baseball bat, that's all cellulose, right? And that is just, cellulose is a long polymer of glucose, right? Glucose, all bonded together. So there's a molecule of cellulose. There's another molecule right underneath it. Maybe it's a little longer, and then another cellulose underneath that, a little shorter, random lengths in there. But they're all real tight to each other, and it's cellulose. Each molecule has 5 hydroxyl groups. Guess what the intermolecular force between 2 cellulose molecules is? We just talked about it. Hydrogen bonding, and you add up those forces, and now you have a tree that will not be knocked down in a hurricane. And that's not bonds holding the tree strong. That's intermolecular forces. So individually, they're tiny, right? But when you have a lot of them, they add up. And you know what's even more important about intermolecular forces? We don't talk a lot about trees here. As magnificent as they are, we don't. I love them, but most of us are here for like health-related reasons, right? Medicine, pharmacy, dentistry. The most important thing about intermolecular forces it's where molecules go in your body. Make sure you get an activity there. So it's all about polarity, right? Polar molecules don't like associating with non-polar molecules. They don't have similar interactions. They love things that are like themselves. So if you take a vitamin like vitamin A, the vast majority, every bond in that molecule, 90% of them is non-polar covalent. So it's a molecule that's non-polar covalent. Where do you think vitamin A ends up long-term in your body after you ingest it? If it doesn't have any polarity at all, it ends up stored in your lipids, right? It's called your adipose tissue, if you want another name for it. Everybody's got it. Even the thinnest person you can find has adipose tissue. They better, because a lot of important stuff happens there. Okay? Now you take a vitamin like vitamin C. Vitamin C, the vast majority, well, not the majority, but a lot of bonds are polar covalent, and some of them are OH. When you have OH, you think that thing doesn't want to go anywhere near a lipid, right? Where does it want to associate? What part of your body? Where's the aqueous portion of your body and things moving back and forth inside your body? Blood. Good. So vitamin C gets quickly into your bloodstream. It's all about intermolecular forces, right? Solubility is all about intermolecular forces too. Okay, so vitamin C in your blood, and you know something about your blood, it filters every few hours, right? Through your kidneys. So we pass vitamin C out of our system quickly, all because it's in your bloodstream. And vitamin A hangs around for months. It can, because adipose tissue is not in a freely circulating area. It's like kind of isolated. And it's things that get there stay there, because they love the adipose tissue and there's no flow in there. Well, very little. So it's important concepts. Here we're just talking about the one concept called boiling point. Yours will be boiling point, but all physical properties. Thank you. I couldn't come up with the word property. All physical properties are based on intermolecular forces. So we already talked about the strongest of the intermolecular forces, called hydrogen bonding. And some of you have seen a video or two that I've brought up hydrogen bonding, and I'm never happy, am I? What am I always saying in my videos when hydrogen bonding comes up? Because I'm going to say it again. It is the worst mistake in chemistry teaching history to call it what they called it. It causes so much misconceptions of chemistry. One, students think when you're breaking a hydrogen bond, you're breaking a bond because you just said, I'm breaking a bond. It's wrong. You're not breaking a bond when you break a hydrogen bond. What are you breaking? An intermolecular force. Well, what's the difference? Well, a covalent bond holds a molecule together. An intermolecular force holds molecule A close to molecule B, and it's nowhere near as strong, yet you learned it to be called a bond, so you think it's as strong as a bond. It was a mistake to call it that in the first place, and misconceptions are just bred the instant the mistake is spoken the first time. We can't get past it. And we're so entrenched in using this misconcept that it's going to stay until a brave young person comes around and says, you're actually hurting learning. It needs to change. It's not going to happen in my lifetime. Okay. Big speech. So hydrogen bonding is not a bond. Call it an extreme dipole. Then every definition I ever give is just dipole. And we have degrees of dipole. Why is it extreme? One, hydrogen when it's bonded to oxygen, or hydrogen when it's bonded to nitrogen, or what's the third one? Hydrogen when it's bonded to fluorine, and those were real bonds you need to be talking about. When that exists in a molecule, that hydrogen is a candidate for hydrogen bonding with another molecule. Which atoms in the other molecule are the only candidates? They've already been mentioned. O, N, and F. F, we're almost never going to talk about because it's very specific. The only molecule you can talk about with F in it that hydrogen bonds is the one molecule, HF. It's not organic. It's a gas. Okay? It's dangerous. We don't talk about HF. So in our course, we talk about hydrogen bonding. And guys, we're learning functional groups. You're restricted to H bonded to N and H bonded to O. F is not organic. Yes, it would be a hydrogen bond if we had F. So what are my functional groups that can participate in hydrogen bonding? Alcohol, for sure. It has the H bonded to O, so it can be the hydrogen bond donor. And the other alcohol molecule has the O, which can accept. And she said, amide, I have to agree partially. I'm going to give her most credit for that. I would agree with her saying the primary amide can hydrogen bond. Has an H bonded to N. The other molecule has at least an N, right? If it's an amide, it's got an O. So that O can hydrogen bond with the H, and the N can hydrogen bond with the H. I would say secondary amide, she was good too, but I will not give her credit for tertiary amide. Why not? There's no H on the nitrogen. If you're tertiary nitrogen, you have 3 bonds to carbon, right? You do not have a hydrogen, you cannot hydrogen bond. And I'd like to remind you, ammonia, although it's not an amine, has the same chemistry as amine. It does the same stuff. So ammonia is definitely a hydrogen bonder, right? We knew that a long time ago. Okay, so we got amides, we have alcohols. What other functional group can hydrogen bond? Carboxylic acid, intense hydrogen bonding, because it's got everything. It's got the H bonded to the O, so that it can be a donor. It's got the carbonyl oxygen for molecule 2 that can be the acceptor, right? Or the other oxygen in molecule number 2, right? The OH oxygen can be an acceptor too. So it's got extensive hydrogen bonding. If you see a carboxylic acid as one of your molecules, I need to see the words extensive hydrogen bonding before you make it the highest boiling point. Remember that. Carboxylic acids, if all other factors are equal, are going to have the highest boiling point, because that's an extreme dipole without hydrogen, and there's lots of places to do the hydrogen bonding. Any more functional groups that have hydrogen bonding? We had all the amides except for tertiary. What about the amines? Same story, right? All the amines except for tertiary just don't have a carbonyl, so it won't be quite as strong a hydrogen bond, but still a hydrogen bond. Is that it? I think that's it. For what we know so far. Now, an aldehyde or a ketone, they don't have the H for hydrogen bonding, right? But if you drop an aldehyde or a ketone in water, water can donate the hydrogen for hydrogen bonding, right? And the carbonyl oxygen will accept that hydrogen. So it will hydrogen bond as long as another molecule can provide that proper hydrogen, but not with itself. So a boiling point question, there's nothing else present. Aldehydes, ketones do not have hydrogen bonding available, right? If it's just an aldehyde or a ketone in there. But they do have a polar carbonyl, which we just talked about, right? So that's the second strongest intermolecular force. You got carbonyl in molecule 1 with carbon and oxygen, slightly positive carbon, slightly negative oxygen. Molecule 2 is going to come in the other way, right? To put the carbon near the oxygen, and the other direction, oxygen near the carbon. So, and that's called a dipole, right? So you need at least a polar covalent bond. And if you have that, you are now a dipole candidate. Now that would be canceled if the two dipoles canceled each other, right? If one dipole straight to the right and the other's to the left, then there's some canceling as dipole there, right? Keeping that in mind. So dipoles, we're talking esters, aldehydes, and ketones. Those carbonyl ones that can't hydrogen bond. Tertiary amide would come back, right? But not tertiary amine. Tertiary amines aren't polar at all. We have a tertiary amine on here? No. We have secondary and primary. We'll talk about those. We haven't started this question yet, have we? Well, we got a good background. So let's start this. And do you see any hydrogen bonders? Because that's where you need to go first. Hydrogen bonders. 5 he likes for hydrogen bonding. Oh, that's the most extensive one, isn't it? Carboxylic acid. Explain. V has the most extensive hydrogen bonding, which is really an extreme dipole, but I don't want to get my blood pressure up some more. So next best would be an alcohol, but I don't think I see one. Do you? Not in this example. I got to go with hydrogen bonding amines next. Okay. So I've got molecule 3 and 6. Is that right? Highlighter, different color. 3 and 6. And that was 5. So 3 and 6. Ooh. Have next strongest H bonding. So I need those listed before V, but I maybe I can figure out which one's a little better than the other. Yeah, maybe. It might be 3. It might be 6. Now there's something I need to look at first. The size. Size is another factor. We didn't talk about it at all. But it's the third intermolecular force, the one we never mentioned, but it's the weakest. What is that one? London forces. And those are not, they're dipole, but they're always changing. They're ephemeral. I like that word. Ephemeral. That's your London forces. London forces. Ephemeral dipole. You're saying, wow, I give up. I don't know what ephemeral means. It's just another way of saying temporary. Transient is a good one to say. Okay. Short term. So it starts out weak dipole, and then it changes, and it's not even the same dipole in a nanosecond. So constant flux. And that's not really part of my answer. That's just a reminder what a London force is. And the H bonding. Bigger molecules have higher London force. Okay? That's why candle wax, which has no polarity at all, none, is a solid. I mean, look at it. It's candle wax. It takes a lot of energy to get it to be liquid, right? You gotta heat it up. Well, those London forces add up because the molecules are like 30 carbons long sometimes. And every bond contributes to the London forces, right? Okay. Next, we got to figure out which one's better, 3 or 6. You'll see when you watch videos in this type of question, I'm always counting the number of heavy atoms. Number of heavy atoms. Now, in this course, it's just anything close to carbon. Carbon, nitrogen. Well, I didn't even write carbon. I said carbon, didn't write it. Carbon, nitrogen, oxygen are our big heavy atoms. So in molecule 3, there's a nitrogen and 6 carbons. That's 7 heavy atoms. It's in purple. 7. And in this one, it's 1, 2, 3, 4, 5, 6, 7. It's also 7. So that's not a variable. 7 heavy atoms, not carbons. If one of those was 8, I'd say we have a winner. But we don't have a winner. So now I got to pick the one that seems to have a little more hydrogen bonding than the other. Which one might have a little more hydrogen bonding than the other? Because it's got more hydrogens attached to nitrogen. Okay, 3. 3, a little stronger. Because more H's capable of H bond. You can't just tell me it has more H's. Ladies and gentlemen, they both have the same formula. You just say more H's, you're in trouble. It has the H's of the right type. They're bonded to nitrogen, right? So I'm going to put 3 a little higher than 6. And then I'm going to ask, oh, we have a question first. Absolutely. I'm looking for excuses to give you partial credit. I am always. But in particular, this type of question, one, English is not a lot of your first language, and I know this. So I'm looking for clues, like picture clues. That you're illustrating that you understand the concept. Even I'm a fan of pictures in chemistry, particularly because it's all pictures. Okay. Yeah, you're going to get partial credit. Nomenclature, I'm always looking for excuses to give you a partial credit. So give me something that's right. Okay. Yeah.
Would we not look at branching when we're deciding the...
Okay, now she's brought up branching. Branching is only brought up near the end of this whole thing, and you're only allowed to talk about branching if the intermolecular force nature is identical, so similar functional groups, and the only difference after that is size. Okay, sorry, and the size is the same, and the only difference was branching, what I should have said. So, one, you can't compare an alcohol to an alkane and say, oh, because there's branching in this alcohol, it's going to lower the force below this alkane. No, there's very few alkanes with lower intermolecular force than alcohols because of the alcohol. Okay, that is a factor that beats branching by a mile. You know, it's like there's a 300-watt light bulb there, and one guy's saying, wow, that's a bright light. The other guy's saying, look at that mosquito. He's real close, and all he sees is the mosquito, not the 300-watt bulb. He's not talking about the big picture. Okay, that was a terrible example. I'm sorry. Question now is, are there any molecules that have dipole attraction? They have a polar covalent bond that doesn't get canceled when you do the net dipole vector. What? Do you vaguely remember us doing one exercise on net dipole vector and forgiving yourself for not remembering, because the next thing Dr. Whitaker says is he's not ever going to put this on a test. I know where we're coming from. But, you know, if you have something like this that has very polar bonds, you shouldn't be trying to tell me the molecule's polar, should you? They canceled. So just because you have polar covalent bonds doesn't mean you're a polar covalent molecule. Okay? So doesn't belong in this question, but illustrated a point. Now, why I brought it up, I will show with something more similar to stuff we see. The one that's my favorite is a tertiary amine. Remember, we already ruled it out for hydrogen bonding. That has roughly the same intermolecular forces as that, because even though this is a slightly polar covalent bond, it's going in 3 directions, and I know there's a lone pair. That means they're not like canceling, but they're pretty much canceling. I mean, they're canceling for the most part. tertiary amine should be treated like an alkane. You'll see at least 2 videos with that. He groups a tertiary amine just like it was an alkane. Well, that's an alkane. And that's a tertiary amine. And I know it isn't for this question, but you know, on more videos than not, there's a tertiary amine. I'm serious. Don't just watch one video on the same type of question. So not relevant for this question, but shows up on a lot of other videos is all I'm saying. And we do have an ester here. We have an ether here, but I'm going to show you the same point I illustrated a moment ago. There's your ether. This dipole almost cancels this dipole, right? Almost. There's a little up that didn't get canceled, but it's almost trivial with ethers. Ethers, dipoles, almost cancel. So similar BP to alkane. When I say alkane, you're just thinking C's and H's, right? I hope. You should be. So please don't talk to me about dipole, and ethers, but on esters, they're not canceling, and on ketones, they're not canceling. And I believe we have both. You got to verify to yourself. That's not an ether. It's not obvious that's not an ether. It's an O in the middle of a chain. When it was an O in the middle of a chain here, I mean, this thing could have been written out with the O in the middle of this chain, and it's not the same as this O. If you try to put that O in the middle of a chain, you'll have an octet violation or formal charges. You cannot make the molecule work because that's a carbonyl right there, and that's the only way to make it work. And if that's a carbonyl right there, this carbon to the left of the circle, then that's a ketone. So VII, comma, IV, both have dipole because of polar covalent C-double-O. That's just a fact. Can we do an atom count on those 2 molecules? VII and IV, heavy atoms, that's carbons and oxygens. So VII 1, 2, 3, 4, 5, 6, 7. So it's another 7, a lot of 7s, we like 7. And that was that, and IV is 1, 2, 3, 4, 5, 6, 7, 8. 2 oxygens. 2, 3, 4, 5, 6, 7, 8. We have a winner. I don't want to talk about branching or anything because they're not the same size. If they were both 7s, I would be talking about these 2 methyls branching. If they were both 7, then branching will be a factor, but it's not. So I'm just picking the heavier IV has more London. And you show me what the consequence is when you put IV after VII in your answers. Heavier IV has more London. That's a good enough sentence for me. I don't need proper sentences. You got the concept in there. Now we're just choosing 3 more, and I believe they're just alkanes or alkane equivalents. So London only, I need the space here, so. London only are our weakest And that's definitely number 1 and 2. And an ether behaves like an alkane, just like a tertiary amine. Put them all together, people. Ethers, alkanes, tertiary amines, they are considered first principles equal. Okay, and ether is VII, triple I, sorry. And let's do a number count because that could narrow out 1 or 2 of them. First one, 1, 2, 3, 4, 5, 6, 7, a lot of 7. Second one, 3, 4, 5, 6, 7, 8. I'm trying to trick you with that one. I'm admitting it. I want to see students say that 2 has a lower boiling point than 1 because it has more branching. And you'd be wrong. And you're not wrong because you have more branching. Right? The London forces of 8 is going to beat the London forces on the 7 every day of the week. It never got to the branching for distinction. Let me put it another way that some people understand numbers better. If you go from a molecule like butane to pentane, straight, simple molecule, only different by 1 carbon, right? Your boiling point changed by about 30 degrees. It's a rough approximation. Somebody's going to look up the data and say, it's way off on that estimate. But in general, if you're comparing hydrocarbon 1 to hydrocarbon 2 and the difference was only 1 carbon, your difference is 30 degrees. Now let's compare butane, boiling point roughly 0, to isobutane, boiling point like -4. What kind of a change was that? By introducing a single branch, a change of 4 degrees Celsius. Is that competing with a change of 30? Why do we not care about branching if the number of heavy atoms is different? Because that changes 30 degrees Celsius. By adding a new heavy atom, the London just increased that much. Okay? Branching only changes things a few degrees. It's always the last thing you look at, and never even look at it unless you have the same size, like mass, and the same forces. If one's a dipole molecule and the other's a hydrogen bonder, I don't want you looking at number of carbons. Those are factors that are much more important. I'll give you an example. Methanol, 67 degrees Celsius. Ethanol, 76 degrees Celsius, 78. Ethanol versus acetic acid. No, I should go with methanoic acid, which is formic acid, because they have the same mass. And you went from 79 for the ethanol, formic acid, you're getting close to 100. And that's just changing from dipole to hydrogen bonding. And that was a huge change by changing the force, not even the size. Okay? A lot of talk. So 1, 2, and 8. 8 has a size 7 as well. So the 8 is the winner, and you're going to say that by putting 2 here. 2 has highest mass. That increases London. And what about 1 versus 3? 1 versus 8. 8 has look at, I drew 8 out right here. It's straight across, isn't it? This has a branch and they have the same size and similar forces. If you're branched, what does that do to your intermolecular forces compared to unbranched? Decreases. Here's my example. It's the most boring demo ever. 2 branched molecules compared to 2 unbranched molecules. I hope that's not an active quiz. Oh, it's old. All right, which molecules are closer together as a pair? I mean, these are touching all the way. That is nice intermolecular forces there, right? There's a lot of contact. These, they're only touching near the edges here, and all around the outside here, there's nothing and nothing. If you're branched, you're more ball-like, right? You have lower intermolecular forces, your boiling point goes down. So we're going to say that. We're going to say 1 has similar forces. 1 has similar forces and size to 8 branching lowers London, because the molecules aren't as close to each other. So branching is found in 1 and not found in 8. And there's your final answer. I hope we have all the ones represented. So in the boxes only, that's all I need. And we're done with that finally.